At one end of the scale, over here, we have the quantum world. With all that juicy subatomic goodness, wave-particle duality, Heisenberg uncertainty principle, just Schrodinger's equation, Dirac, blah, 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 blah. Juicy stuff. And it governs the behavior of quantum systems. And on the other end of the scale, we have the classical world. We have electromagnetism and Newton's gravity and thermodynamics. You know, all the rules of everyday classical physics. Where does one start and the other end? And perhaps a more fundamental question is, obviously, the rules, the classical rules of physics don't work in the subatomic realm. That's why we had to go and invent quantum mechanics. But do the rules of quantum mechanics govern the classical world? Like if I throw a baseball to you, I can describe the behavior of that baseball using Newton's gravity and atmospheric drag and all sorts of classical physics. Can quantum mechanics tell me how that thrown ball is behaved? Can quantum mechanics govern or give me predictions for the classical world? It obviously doesn't go the other way. Classical physics can't describe quantum reality. Can quantum physics describe classical reality? The answer is we don't know. And there are very, very good arguments back and forth. One of the first people to argue against this idea was Niels Bohr, one of the founders of quantum mechanics. And in the early 20th century, as everyone was putting the pieces together of quantum mechanics and just figuring it all out, he made a very, very clever observation, very astute observation. And this was linked. He was best friends with Werner Heisenberg. Heisenberg was developing the uncertainty principle, what would become the uncertainty principle, and he was communicating back and forth with Bohr. Bohr realized that this uncertainty principle was part of a larger framework. He realized that in the quantum world, everything comes in pairs. That the quantum world is best described as pairs of complementary properties, like wave and particle. It's impossible to talk about a quantum object as purely a particle or purely a wave. You can only talk about it as a unified, complementary thing, a wave, particle, or pave. Neither of those. Wave-particle duality, we'll stick with that. And just like the Heisenberg uncertainty principle, there's properties of the system like position and momentum. You can't know precisely both position and momentum. They're linked together as a pair, and the more you know about one, the less you know about the other. There's a pair there. Bohr argued that the classical world of classical physics, up here in the macroscopic world, everything's unitary. Everything can be just a particle or just a wave. You can know position and momentum precisely, infinity, like perfectly, but that doesn't apply to the quantum world. Quantum world operates under a different set of rules, and the quantum world can never match the classical one because it's a different set of rules. That you can never get classical physics out of quantum mechanics. Now, you can match the two. You can match quantum mechanics to classical physics, and we do this through another one of Bohr's ideas called the correspondence principle, which is that when quantum systems become large, for some sense of the word large, and it's defined in various contexts, they begin to melt away and merge into the classical physics. So that if you have, say, an electron orbiting a nucleus, when the electron is close, it's quantum all the way. But if that electron has a lot of energy and it's orbiting far from the nucleus, then it just looks like a normal two charged objects orbiting each other electromagnetic problem. Bohr proposed this correspondence principle as a way of guiding the formulation of quantum mechanics. Like, oh, if you want a quantum theory of the universe, then at some point that quantum theory should give way to a classical description, but it doesn't necessarily replace the classical description. It's not necessarily true that you can have rules of quantum mechanics, the physics of quantum mechanics, that give you all of classical physics back. Just like you can't use classical physics to make quantum predictions. The correspondence principle allows us to piece these two together so that you can have a quantum world and a classical world, and they somehow connect together. So you have an overall description of reality, but they're still two separate sets of physics. So do we live in a quantum world? Am I governed by quantum mechanics? Are you governed by quantum mechanics? Niels Bohr would say, no, you're governed by classical mechanics. Quantum mechanics is valid where it is in the subatomic world. It's not valid up here in the macroscopic world. Other interpretations of quantum mechanics disagree. They say that, yes, you can formulate all of the classical physics in terms of purely quantum concepts. Who's right? Who's wrong? We don't know. Do we live in a quantum world? Let me know. Thank you so much for watching. I hope you enjoyed. You know what to do, right? Like, share, and subscribe, and go to patreon.com/PMSutter. That's PMSUTTER, like my name, Paul Matt Sutter. That's my name, to help keep these shows going. I really appreciate it, and I'll see you next week.